Hey guys, this is Jan from DoraHacks and welcome to our Hack AVS Empower the Eigenlayer Restaking Ecosystem workshop number 4 today, which is about the Lagrange zk-coprocessor verifiable database to every smart contract. Before we start, let me give you some background on this hackathon. As the largest Web3 developer incentive platform, it's an honor for DoraHacks to support and host the Hack AVS hackathon, and we're looking forward to seeing all the incredible projects building on top of the Eigenlayer ecosystem and on top of Lagrange. So today we're happy to have here Jonathan. He's a smart contract developer, and Nicolas, head of engineering at Lagrange Labs. So without further ado, let's welcome them to start. And for the audience, if you do have any questions in the meanwhile, feel free to drop them in the comment section on the YouTube or Binance Live chat room. So feel free to begin once you're ready.
All right. Hi, everyone. I'm Nicolas. I'm leading the engineering efforts at Lagrange about the zk-coprocessor that we're building here. So I'm going to explain what it's doing and how it works underneath. It's going to be a pretty technical talk, but like this, hopefully at the end of this talk, you should be able to understand what's happening in Lagrange. So basically, our main goal is to be able to let any smart contracts be its own database and be able to query this database from the same smart contract, or any other user can query this database. What this database is filled with is just historical on-chain data. So, for example, take a very concrete example. You have a mapping that stored the NFT ID to its owner. Then at each block, we're going to record it in our database, and then you'll be able to query it. You'll be able to query it for historical value. So how many NFT IDs has this guy exchanged in the last few blocks, or 100 blocks, something like this. We're going to go more into details down this chat. So right now we just released V0, which is named Euclids last month actually, which is exactly doing this. It's exactly returning the set of NFT IDs that our owner has had for the last X block, and we can customize the blocks. We can customize the owner address. This is it's important to note at this stage that this is the first public release we are doing with this technology that we're going to present to you, and our goal is to extend this to have generic queries that user can write their own queries, like SQL basically. And we're going to see more example of this down the line. But basically, our goal is to be able to let everyone query via simple language such as SQL. We're targeting SQL right now, to be able to target historical contract on chain very easily. So how does it work behind the hood? What's the flow, let's say, that to interact with to be able to give a database to a smart contract? So it operates in 2 stages. The first is the pre-processing, where a smart contract needs to say to Lagrange, hey, I have these variables, these storage slots. Can you index them in your database? Okay, and from this moment onwards, Lagrange network is going to look at every block. It's going to look at all the variables of this smart contract that are interested to index, and it's going to put them in our own database. Okay, and we're going to do this repeatedly at every block. The second stage is now we can query over it, because this database is special. It's not just a SQL database or a dump file. It's actually a zk-friendly database where we can actually query over it and give a proof that we have really run the query correctly in an efficient manner. Okay, and so we really separate the part where we prove the origin of the data that we put in our database to the part where we query over the data. Okay, these are 2 distinct phases. And by doing this separation, we allow ourselves to be way faster than everything you can find elsewhere, and in the term of the query, because we are transforming the data in a proof-friendly format. Because for those who know and are deeply expert in how EVM works and storage works, the MPT, the Merkle-Pareto trie, is fairly complicated, has many small tweaks and many binary operations, which are very expensive in the proving system. And so we want to do all this expensive operation only once, such that we can be very efficient at query down the line. So that's what I was mentioning first, the indexing phase or the pre-processing phase. We take from the blockchain every block that comes. We look at the storage trie of some smart contracts, okay, and we are computing some proof here that we really looked at some data and they belong to this smart contract and they belong to this block header, which is as number I, for example. Okay, and we have a proof that we extracted some data. It's basically Merkle MPT verification proof. And most of you here should be familiar with it. But then from this, we prove that we're constructing another tree, a completely separate tree. But this tree is a regular Merkle tree, such as you know, with like nice properties for zk friendliness. Let's say it's using a special hash function, and here we prove that we put exactly the same data in the leaf of this tree than in the storage trie. Okay, so we really prove the equivalence between these two trees. But even though these two trees have two different structures, we can prove they contain the same data. That's the key part, and we're going to look into how do we do this later on. But that's the key part that allows us to put this into this zk-friendly database. And again, just to repetition, we do this at every block. So every block, we have to prove the values of a smart contract, they belong to this MPT trie, and then put it in our storage trie. And then we can query over it. Now we have a very simple and elegant, let's say, Merkle tree construction, and it's about querying over it. And we're gonna look more in detail what it means later, but we're gonna use the MapReduce framework where we can actually, for each layer of the tree, we can do operation in parallel. And you have to think that each node in the tree is a proof itself. So that means we have a prover network that is ready to take task and submit proof. And they're going to test each task for each node here that I can show in the tree. So for example, for a very simple sum operation, there's going to be one operator, one worker that's in our proving network that's going to operate under the node which has contained the value 1, V1, another one for V2. We're going to generate proof. And then we're going to generate a proof where we aggregate these two things together. Okay, so now we're going to add the results of these two proofs together. It's very similar to the MapReduce framework, where instead of bringing all the data to one big server and you run the computation, you run partial computation on partial set of data which are hosted in different servers, and then you aggregate the results in parallel together, and everything can be done in parallel. We're going to go into more detail down the line, but basically this gives you a hint of why we can be very fast on integrations, because basically we can be horizontally scalable. That's one of the key properties that Lagrange proving network has, is to be very efficient to answer queries by being horizontally scalable. And we go over the tree, and at the end we get a proof of the computation. We added all the values, and we submit this proof back on chain. We're going to see the workflow right now, actually. So how does it work? Then, like I said before, the smart contract developers need to index his contract to Lagrange network. So we need to do indexing requests. Right now, for the current V0 that is out, we support mapping types. And for V0, for V1, for the upcoming V1, we're gonna support basically the native types, the mappings, the arrays, these kind of things, and we're gonna create real table in the SQL format that you just can have a look at and be able to just write SQL queries on top of it, basically in a native format. And then once you've done this request to Lagrange, then again anybody can query your database. So they go back to Lagrange, they ask Lagrange contract, hey, query this database with these parameters, and then it gets off. We look at via an event, we do our proof system, we do the aggregation of proof, etc., like I showed you before, and I will go into more detail later. And then we send back a transaction, really Oracle-like model. We send back a transaction that gets back to the contract that asked the query, and then it gets the results. So it's really in two stages. But really the indexing request is for developers that want to expose their database to on-chain, and the query request is for anyone to query any database that is already present. We're going to look into more detail down the line with Jonathan, who's going to do a nice demo afterwards of what it looks like. So I don't want to spend too much time on it, but basically right now we do require some little tweaks on some aspect of the solidity contract, but we are trying to standardize at a standard. Like they think like ERC20 is a standard, but I think we're working on the world having some kind of Lagrange standard. One thing, for example, is the mapping. how do we want to prove a mapping entry? So as you, maybe most of you are well, you can't get the length, you cannot really get the number of elements in the mapping, and you cannot get the length for the mapping, basically. So because of this, because we, in our proof, we want to show that we really looked at all the elements of the mapping, we need to get somewhere the length written down for us. Okay, and this is how we enforce it right now, but we need to enforce that the mapping is associated with its length. There's a length variable as well. It can be also another array which tracks the length. It can be many ways to do it, but right now this is how we're enforcing it, and we may be able to remove that assumption down the line. But I think this is right now what we have to work in. For basic types and arrays, we don't have this restriction, so it's free to use and for any already existing contracts. To register, it's very simple. You have these registry contracts, and again, Jonathan may be able to show you down the line after. That is the Lagrange registry, and you say just register. This is my contract. These are the storage slots about the mapping, and this is the storage slot about the size. Okay, and so that's it. Once that's done, then the Lagrange network will pick it up. Right now, we are still in a mode where we are permissioned about the contract we are opening up, because it does require quite some proving resources behind to index the database at every block. So we don't want to let anyone just be able to use up our resources, but the goal is to be able to open up very soon. And right now, yeah. And then we go to the crewing phase, where basically, simply enough, again, we have the Lagrange registry, and then we do a request where we say, hey, it's about this contract, it's about this order of the NFT between this block and this block. Okay. And offset is like really they need to think about in SQL format, because this is what we ideally want the user to just deal with, not this calls here, just with SQL queries, where the offset just gives you a from all these results, and it's limited to 5. How many? What is the site? Where is the window where I want to look at on the results? And then the result gets processed as a callback. So once we've done the proof, we'll call back the contract that called this query with the request ID, because there's always a request ID associated, and the results. All the results are treated as UN256, and then it's up to the application to interpret this. We'll be able to make some nice wrapper pretty soon to have a better API about this. But with this, we can already do some pretty cool stuff that we'll show you later. Again, this is like very specific to V0. We are working on V1, which is going to really change the game drastically by being able to just type SQL queries. So now I want to go into a little bit more detail into how it's work. Once we've seen basically the high level, the developer workflow, I want to go a little bit into really what's going on behind Lagrange, because it may seem like there is a magical thing, oracle thing that is behind, but actually it's fairly complex, and because we use proof system, you can be guaranteed that the result is correct, but you need to understand as well how does it work underneath. So we basically need this database. I hinted before that we want it to be zk friendly, so it's really fast to compute some proof over this database. Horizontally scalable. When I spin up more machines, it should be able to compute the proof faster, and efficiently updatable. This is a very key point for us, because remember, we are indexing all the historical data. So for each block, we have to make some proof. And imagine right now, for example, for V0, we are indexing the Pudgy Penguin NFT contract, and there's like 8,000 of NFTs here. So imagine we'd have to prove 8,000 entries at each block. It will be very, very expensive. What we do instead is we prove once the 8,000 entries, and then we only prove the updates. So if somebody changed ownership from an NFT to another, or he sold his NFT, then this is an update, and it will get propagated through the tree. But we only need to prove these updates. And we're going to see how it looks like just in a minute. But this is very important for us to be able to amortize the cost. And we take the assumption here that between two blocks for a given smart contract, the entropy, the difference between the first block and the second block, might not be so high. And so we pay much less to scoring all this historical data. So how do we do it, actually? How do we compute, how do we get this efficiently updatable property? So it's going to get a little bit technical, but stick with me and we should be able to get to the end. So basically, imagine we have a regular Merkle tree here, right? So the value, we have 1, 2, 3, 4, 5 as value as value in the leaves. So if you were using a, let's say, regular proof system, like the one you maybe have heard of, like Plonky 2, Plonky 3, even SP1 or this thing like this, then you would just give the whole tree inside the proof system and you say, hey, prove that the value 1, 2, 3, and 4 are in this tree and compute this sum of these numbers, for example. Okay, you could be able to do this. The problem is not scalable at all because first you need to give the whole tree. Okay, and that's the tree for us may be huge. Like we're talking about 8,000 entries per block. So over 100 blocks, you can already grow to 8 million entries. So and it keeps growing. So this is not workable for us quickly. And also we don't have a nice update property because if something updates, imagine the value 3 becomes 8, then normally you can see the blue stuff here. That's the path that got updated in the tree. But if you use a regular proof system, that we have to give again the full tree and prove that 8 now is this thing, but we need to also prove 1, 2, 3, and 4, 1, 2, 8, and 4. And basically, we have this computation which is O of n, and this is not workable for us for the reason I explained before, right? So that's the problem here. But by using a regular proof system and you write a secret in Circom, whatever familiar tools you're familiar with, then high chances is that you're gonna get into scaling issues. So how do we deal with this? Well, the key trick it comes from Recall Trees, which is a paper written by by Vincent Shravan from the research team in Lagrange. Is that instead of feeding the whole tree to a single proof system, we're gonna do the opposite. We're gonna do a small proof at each node of the tree. Okay, you really reverse the paradigm. It's like MapReduce. Instead of bringing all the computation to one big server, you bring the computation to where the data is and you compute over partial data. Here it's exactly the same. So we're gonna do a proof just for the node 1 that prove that, hey, I've seen the data that is contained in this node, and I've hashed it, and the output of this proof, there's always an output in the proof, is the hash of this node. We do the same for 2, okay? And now this orange stuff at the first layer is gonna take as input these 2 proof, and it's gonna look at the hash of these 2 proof, and it's gonna concatenate it, and it's gonna itself expose a hash. So basically we use a proof recursion here. I don't want to enter too much detail, but but that's the key property here that we use. So again, we don't feed the whole tree to a big database. We just take very small proof at each node of the tree. And that may seem a little bit weird at the beginning when you think, well, why do you want to do this? You clearly incur more costs because like doing many proof, it seems strictly worse than doing one big proof because you can amortize the cost and things like this. But it actually turned out that not really, because it gives us the nice property that we can update value efficiently. So how does it work now? Remember, we have one proof per node, and each proof exposes the hash of basically of the whole subtree beneath it. So this node here exposes the hash of 1 and 2, and the node on the right exposes the hash of 3 and 4 of the subtree 3 and 4, and the top roots, then the top proof exposes the hash of the whole tree. And that's it. That we only need to give this top proof here to prove that we've looked at all the values. And this is the top proof is equivalent to giving the whole tree to the big prover. And now how do we deal with the updated value? Then now it's fairly easy because imagine 3 changed to 8. Then now we have these blue squares, right? You see these blue squares. These are the proof we need to update. We only need to recompute 3 small proof. So basically now the computation we need to do when there's an update is O of log n. Actually, it should be small n to say the big N is the number of leaves, but it should be, oh, sorry. It's O of log n because we only pay the price from the leaf to the roots, okay? And we don't recompute the proof for node 1, for node 2, for node 4, and for the intermediate node here. These, we can just copy them and reuse them. There's absolutely nothing that changed in this subtree here. So that just this trick is able to give us huge advantages over the previous solution when you need to give everything inside a big proof. It takes a while to really grasp the power of this transformation, and I recommend you that you search Rectal Tree's papers on Lagrange website, or just on Google it, and you will find it. And the paper is very nicely written. You can get all the details here, and you will really understand why this construction is very efficient in our case. The nice thing about it, again, is because now we have one proof at each node, then that means the proof for 1 and 2 can be done in parallel by two binaries, by two workers separately in parallel. So now we are, first we get the updated value properties, like the efficiently updatable properties, but we also get the highly parallelizable property, which means like for each layer, we can operate all the proof in parallel. And this changes the game drastically for us, because this is why we are building right now our proving network, which will be able to handle very large scales. And now we can have very large database, but with a proving network that can sustain this load. And the second tool I want to talk about very quickly, it's a bit less detailed, this one, is about the digest translation. Remember, I told you before that we needed to, let me go back here, to transform the data that is in the storage trie for smart contracts, which is difficult to compute over, it's like MPTs, like Merkle-Paget trie thing, to a nice Merkle tree, which is zk-proof friendly. How do we do this? Like, how you could have a one big proof that extract all the values and things like this, but it's very, very costly. And look at both trees in parallel in same big proof. This is very costly. It's not very efficient to do this over. The computation is still O of n and things like this. Actually, 2n now, because we have two trees. So we need to find something else. And the way to do it is by using an improvement over record trees, which use digest translation. What we call digest translation is based on a paper from Sinat Sethi from MIT, which was used for authenticated data structures. And basically, it allows to have an accumulator value. Think of it as a hash function, but that doesn't care about the order where you insert stuff. For example, if I hash 1, 2, and 3, it will not give the same hash as if I hash 2, 3, and 1. Okay, but by using this special hash function, this digest translation, which is called multi-set hashing, we can get this. So now the order doesn't matter. We can get this property. So it's basically a very efficient way to represent a set where the order doesn't matter. And so now all we need to do is we need to compute this digest of the values 1, 4, 3, and 2, whatever the order is. And then now we can prove we have exactly the same value in our tree 1, 2, 8, and 4, which is not a LPT tree. Okay, and so you can see the digest D here. It's very small, so we try to increase the size, but you can see the digest D here is the same on the MPT above and the same in our Merkle tree down at the bottom. Okay, even though the order is different, the structure of the tree is different, we've been able to compute the two digests, and then now we just need to show their equivalence. And so that allows us to pass from one tree to another, regardless of the structures. And we're also using this super powerful tool to build SQL queries, because in SQL, for those you know, when you do a select, you're basically creating a new virtual table, and then you can use this new table in subsequent queries. Well, that's exactly what we're going to do there for digest translation. So we really need this tool to be able to handle transformation from one tree to another tree, where we only select the NFT, the owners which have been processing stuff for the last 100 blocks, or anything like this. The queries we can do here are just limited by in the imagination, basically. So let's move on a little bit, because I think about time. Yeah. So just to give you just a little bit of step back here, what we want to do, we want to prove the inclusion of values inside MPT trees for specific contracts, and we prove the same inclusion of values inside another tree. Okay, and we can prove that both trees contain the same value as this digest translation, and we can both update both trees efficiently via record trees. Okay, because we do a proof at each node. And that gives us basically all the properties we have. So we do have this one-time indexing cost where we need to prove all the data of the contract, of the storage slot of interest. But once that's done, we only prove the update. So if there is no update between one block and the subsequent one, then we basically just need to copy the root proof of the tree, and that's it. We're good. We don't need to change anything inside the tree because there's been no update on the values. And then it gives us a cheap and fast querying cost because we can do things in parallel. And it's highly, parallelizable, like I said. This slide, maybe I just very quickly on hit. But
sorry to interrupt you. Could you maybe try to restart your slides again?
Oh, sure. To restart the screen sharing?
Yes. Or maybe like minimize your picture, please.
Is this good right now or not?
Right now we see still like the first slide. So, or maybe try to close your sharing and then we try it again.
Sure. Let me close. You've seen the first slide since when? Do I need to restart everything?
Yes.
I need to restart the whole presentation?
Or from this slide. So maybe close this slide and try to restart it again.
Wait, let me just open it again. No, but you were at the beginning of the slide?
Yes, so like that's what we saw most of the time. Maybe if you do the...
Is it good now or not?
Can you try to go to this? Yes, now it's very good.
Okay, so I need to restart everything? Okay. It would have been nice to know earlier.
Apologies.
Okay.
Or maybe like run through the first few slides quickly and then, because like your cursor was moving, but then like the slides, we were not sure like whether it's one slide or like, but yeah.
Okay, but you can confirm me that it's working now.
We can see it. No, it's good.
Okay. Do I have time to grab some water?
Yes, please. Yeah. And maybe consider what you would want to share. And for the audience, in the meanwhile, please ask any questions if you have some for now.
All right, let's start again.
Like maybe you can go through the first ones very quickly. Like you don't need to be too specific, and then wherever you stopped, you can continue your presentation. But I apologize.
Maybe it's best if I redo it. I do have time because if I can redo it, then we can record it and publish it. Because yeah. Okay, so hi everyone. I'm just again talking to about Lagrange and how does it work inside, and just to give a bit of context about what we've been building and what we're gonna intend to ship very soon. So the goal is to give a database to every smart contract, meaning as a smart contract, you should be able to query all your historical values of that has been stored in your variables. The contracts variables, and as a user, you should be able to query any other contract database. Okay, even from a cross-chain perspective, it doesn't need to be on the same chain as well. Announcement here, which we just released last month, our testnet v0 named Euclid, where we are first public release of our technology here, and we are indexing the Pudgy Penguins contract, and we can make queries on it spanning thousands of blocks to search, for example, give me the latest NFT IDs that this owner, this address specifically has. And you're able to check it out. Just type Euclid testnet 0 on Google, and you will find all the information there. So again, on the design promises, it works in two stages. First, we need the pre-processing, the indexing phase. So it's about letting the contracts know, letting Lagrange know that I want to index this contract over these variables. Okay, and once we have this information, once the Lagrange network has information, at every block it will look at these variables. Okay, and incorporate them into its own database. So we keep all the historical values for each variables of interest. That's the indexing phase. It's like, think of it as if you create, then insert or update your table in SQL fashion. That's really like injecting data in the database. And then we have the query part, where everybody is able to query this database. And we're going to look into much more details what it means and how that database looks like and what are the really nice features here that makes us pretty fast and cheap to use. The reason why I put this in this slide is to really insist on the decoupling of the proving that the database contains useful information and real information coming from the blockchain. So in the processing phase, we actually proving that this value belongs to this contract at this block header for this block number, and we do it at every block, and we put it in our database. And this is decoupled from the querying phase. Okay, so it's really two separate steps, and this separation of step allows us to run many queries over the same data many times in a very cheap way. Okay, so that's one important point. We're going to see more details down the line. So about pre-processing, how does it work roughly on nutshell? So we have the blockchain, publish new blocks each time. Then we have the storage drive, this MPT storage drive for the contract. It's very difficult to compute over. It contains ketchup, it contains binary RLP decoding and things like this. This is impossible to do in the proof system. So it's really expensive, not impossible. It's really expensive to do in proof system. So what we do is we prove that we take these values and we put it into another Merkle tree, which is proof-friendly Merkle tree, a zk-friendly Merkle tree. And we prove these two trees contain exactly the same data, and we're going to see how down the line. This is really the main magic that's happening in proposing, and we do this for every block. And then we can query over this specific Lagrange database. So, for example, here we have V1 and V2 and V3, V4 values. Then we're going to really aggregate partial. We do like very similar to MapReduce, where you do partial computation. So for those not familiar with MapReduce, it changed the paradigm from when you need to do computation of a large set of data. Usually before 10 years ago, 15 years ago, you used to bring all the data to one server and compute over it. But this is very inefficient and very slow, and it requires super huge machine. What you can do instead is just compute over partial subset of the data in parallel on different machines, because the data is usually on different machines anyway, and then aggregates partial results together up until you get to a final result. This is exactly what we do, following the tree structure that we have in our database. Okay, so you can see for the sum, we add V1 and V2 here, we add V3 and V4 here, and then at the top, we have a proof that we aggregate different proof of subset that we shows we aggregated V1 plus V2 plus V3 plus V4. But we're going to go into more detail in the database down the line. So just here, just a few slides to indicate what's the developer flow. Basically, how does it like to use Lagrange, and we're going to have a demo right down the line after. We have, first we need to the indexing request, okay, and then there's a query request. Okay, so the indexing request looks like this, where basically you register your contract. This is my contract. And basically, right now we only support for V0, we only support mapping types. But for V1, we're going to support native type like simple variable like uint256 for a price, whatever, mappings and arrays. And so you'll be able to specify exactly which plot do you want for Lagrange to index. Because we don't want to right now index by default the whole storage slot, because there might be a lot of information that the developer and the contract might not need to index. And so we want to be customizable at the level of the slots, because it obviously will cost, when there's whole economics behind in place, it will cost more to index the whole full storage than just subset of storage slots. So that's only one call, fairly easy. Once you get the address of the Lagrange contract, you can just call this. And then for about querying the database, then you need to adhere to some sort of interface. It's basically an Oracle model where you just have a callback. So you first ask Lagrange registry to request, and then you need to pay some gas fee to pay for the Oracle response, where you specify where this is the contract I want to query over, this is the order of the NFT I want to query over, this is a start block and end block of when I want to look at the query, because for us, a query is always related to historical data. So the main two parameters are the start block and end block, because we don't want to start proving stuff outside, because we want to limit exactly the cost. And the offset. So offset is just, for SQL, you have limit and offset that goes end to end. Offset is just saying which windows of 5 elements do I want to look at. And so that's the way. Once you run this comment, once you run this transaction, then the Lagrange network will pick it up, process the proof, and then give back a response as a callback mechanism. And your contract will be called with this method here, where the request ID corresponds to the one you created during the query, and then some results here. So right now the results are generic. You in 256, and the application interprets them in the way it wants. We're working on a much better and much more generic framework for V1, which will gonna be where actual user are gonna be able to write actual SQL query on the tables of the contracts, and that will make things drastically simpler and much more powerful. Because right now the query is fixed for first testnet public release, but we're working very hard to get this down the line to support generic SQL queries to let the user write the query they want. And so here are just a few slides about going back again on the details on how does the database works internally. And just this slide is about saying, what do we want? What do we need to build such a system? Like, we want a database which is zk friendly. We want something very fast to operate over. We don't want to operate in the native types of SQL or native type of MPT, microprocessor and everything, because they haven't been thought with zk friendliness in mind yet. So we need something which is fast to operate with proof. We want something which is horizontally scalable, because we are going to process a lot of data. Just to give you an idea, right now for V0, we are indexing the Pudgy Penguin collection, which contains 8,000 NFT IDs. And at each block, we are indexing 8,000 NFT IDs. For, if you imagine already for 100 blocks, then you're already at 800K entries. And the 1,000 blocks, you're already at 8 million entries. So you can see it really goes really fast. The database grows really fast, and we need to be horizontally scalable in the sense that by spinning up more machines, we can handle more load. Okay. And very important third property for us is being efficiently updatable. So at each block, we are basically looking at some values and inserting in our database. But basically, for the next block, maybe only one of these value change with respect to the previous block. So we don't want to recompute all the values that we've seen in the previous block. We only want to do work which is proportional to the thing that changed, really. Because otherwise, we're always going to pay a linear cost. And we're going to see more in detail why. But this is really important for us, because since we are proving things at every block, it really goes really fast. The cost of proving these things and the latency as well. So we want to be as efficient as possible to only prove what really has changed between subsequent blocks. Think of it as a time series database where you just introduce new value, and we never update a given row. Basically, we only keep appending. So the first tool is Recalchi, which you can check out on Lagrange website. It's made by the research team in Lagrange. It went out last year already. And it's a very nice and elegant trick that allows us to get this efficiently updatable property. So how does it work? Basically, when you have a regular Merkle tree where the values are 1, 2, 3, 4, basically, okay? And usually the parent node is h of h1, f of h2 to get the concatenation of hashes like this. If you would do it naively, you would take a proof system, for example, I know for those who know some proof system like Plonky2, Jolt, SP1, whatever you want to name it, Circom, for those who know Circom, and you would just feed the whole tree inside your circuits. And you would just write, hey, we'll just do a Merkle tree verification for value 1, for value 2, for value 3, for value 4, and now I can do whatever I want with these values. I know they're inside this tree, and I'm good. The problem is very inefficient, because this is O of n, right? Because you're basically looking at all the values inside one big proof. And remember, I said we could our database grow very, very fast. So already 1,000 blocks, we're already at 8 million entries. 8 million entries, it will take very, very long time with a big machine to compute this already inside a big proof. So that's not doesn't work for us. It's not possible to go like this for us. So we need to find something else. And this is what Wake3 brings. Instead of having let's skip this one. Instead of having the whole tree inside one proof, we reverse the paradigm exactly like my previous. We just give a proof for each individual part of the tree. Okay. So now instead of so now at the node 1, I have one proof that says, hey, I've looked at the value here, I've hashed it, and this is the hash of the value 1. Okay. And same for 2. And now this proof at the upper layer, this node at the upper layer, is also a proof that's going to take it as input 2 proof, and it's going to output the hash, the concatenation of the 2 hashes. So you can see here, it's a bit, it's not simple to understand this at first, but basically we use proof recursion to achieve this. And what does it give us? We use recursion as a caching mechanism, because now this proof at each node, I can keep them on disk. Okay, I'm fine, I can keep them on disk. And what happens when I update the tree? Well, let's look at it. When I update the tree, now I get, for example, from, well, it should be, it's a new color. So let's imagine it's 8, it's a typo. And now when I update the tree, which proof do I need to recompute? Do I need to give the whole tree again inside the big proof? No, because I'm using record trees. Now what changed? I really need to recompute the proof for node 3 and all the nodes that goes from this node to the roots. So basically now the computation is in log n instead of being n for each update. And that drastically changed the game for us, because remember, at each block there might be a few updates, so we don't want to pay the price only for these updates. And this is drastically much faster than the simple naive ON approach. So we can always, and the second benefit of it is that it's horizontally scalable, because now each proof of this tree at each layer, they can be computed in parallel. So for example, the first time we will compute this proof for this tree, I will compute proof for 1, 2, 3, and 4. But this can be computed totally in parallel by different proving network, by different workers, by different binaries, by different servers, right? And we can move up to the next layer, and this can be also computed in parallel up until we get to the roots. And the roots, it just take the last 2 proofs generated, verifies them, expose the last hash of the tree. And so that's really the key trick that we use in Lagrange database. And there's another nice trick that we use, is remember before I told you that we need to pass from MPT, the storage try in EVM, to our own database, which is more zk friendly. How do we do this? Because if you just hash stuff, then if you hash 1, 2, 3, then it's not going to be the same as if you hash 1, 2, 1, and 3, for example. The order matters. But in the maplet patcher tries, the order is totally dependent on the key and not on the value itself. And so if you update one value, maybe, and if you insert a new value in the try, maybe all the ordering will change and things will get very, very complicated very quickly. So what we do is we actually use a construction that already exists from a paper, it's called multi-set hashing from CNAT study. And it hasn't been used in this way before. And this is the first time I think people are using it in this way. Is basically we have an order agnostic hash function. You can think of it as like this, where if I insert in this hash function 1, 2, and 3, it's the same as if I insert 2, 3, and 1. And it's going to be exactly the same. So now the order doesn't matter. For us, it becomes very easy to update a value, because I don't think the slide is showing it here, because now we can just prove that we have the same value in the MPT tree and the same value in our Merkle tree by just computing this digest in parallel, regardless of the order, because that means the order can change in our database. We don't need to keep exactly the same order. And so by doing this, then now we can prove both trees, regardless of their structure, contain exactly the same data. And so we prove that we correctly extracted the value from the blockchain to our database. That's basically bring the gap to make sure that we really constructed our database from valuable data. At this point, I think I've went a bit into details. Let's move on quickly because, so putting things together, that's what we're doing. take the MPT tree at each block, we compute the digest of all the value of interest, we compute the same digest in our own Merkle tree, and we prove both digests are equal. And then we can run query on it, and we can see that we can run queries in parallel as well, and it's highly scalable because the tree grows bigger, then fine, we can just spin up new machines. And we're working on the whole proving network. We've incentivized to make that scale according to the load. I think I skip this slide, and this one slide is just about very quickly about how does it work internally. Right now, we have this kind of distributed system architecture where you need to think that we need to understand what from an update in the MPT tree, what does it lead to? Like, what do I need to do? Like, how many proofs do I need to do? What's the best way to answer the query according to the query and the structure that we have in things like this? And this is a whole job of the planner and the executor. And then we have this set of workers that just work behind internally and externally as well. Like I said, we are going to open up, we've incentivized testnet, and such that a worker just take a task, compute this small proof. Again, these are all small proof now. We don't have big proof. That's what is really good because we don't need large proving machine that costs way too much on AWS. Now we can actually run this on pretty standard servers and just get back the proof. And we assemble all these proof together to finally answer the query. This is basically how it looks like in a nutshell. And I think I'm gonna send on this. Basically, right now we have right now for V0 we have 8,000 entries, and we're proving 8,000 entries at each block. And we can, I think the performance is a bit slightly wrong here, but basically we are able to answer a proof end-to-end from the contract to contractual to the response in we've been able to achieve in a minute. And you can check on BSC on the Explorer. And I think that's it for me. Yes. Is there any questions?
So far, I feel like there's no questions. So maybe we can give over the mic to Jonathan.
Yep.
Okay, great. No, that was a great overview of kind of our whole system and really the specifics of how the proving system works. I mean, I'm still mind blown just how great the performance is with just this one trick of Rectal trees, right? That gives you the parallelization as well as sort of the diffs, the quick updates. It's really incredible. So anyways, just a bit about myself and kind of what I'll be doing. So I'm Jonathan. I'm sort of lead smart contract developer at Lagrange, working on our zk-coprocessor. I also do some kind of DevOps and infrastructure work, and as well as some work on the distributed system. So I'm going to just do a quick sort of walkthrough and code demo. We're going to deploy a contract on base. It's going to be a sort of client contract. So we're going to integrate with Lagrange. We're going to deploy the contract. We're going to submit a query and do something interesting with that. And we'll see the result sort of on the Explorer. So I'll go ahead and show my screen. Okay. Great. You can see now, right?
Yes.
Okay, perfect. So quick, I'm not going to go too deep into this diagram, but I just thought it was a good thing to show to kind of tie everything together and get a sort of high level overview of this whole system, kind of what it does and how you interact with it. But I think what's important is we'll just sort of look on the left and the right, and because this is sort of like the interface, right, of how you as a developer, interact with Lagrange and sort of how we're getting data and answering your queries. So you can see the left and the right are two different blockchains. We have Ethereum and Fractal, but really it's sort of many to many. But the point is sort of on the left, you can imagine right now it's for V0, we have Ethereum where we are registering contracts and sort of indexing the data and proving, a mapping in that contract. So in this case, in the example, we have pudgy penguins, right? So we're proving that mapping every block. And that's sort of this registration or pre-processing phase. And that's just sort of goes on all the time in the background. And then when you want to integrate, and use this sort of provable database to run a SQL query and do something interesting in application. That's sort of what our demo is going to look at, is really steps 2 and 3 here. And what we're going to do is our contract that we're going to deploy will be on blockchain 2 here, which actually will be base. And it will be reading, we'll be sort of querying data from Pudgy Penguins on L1 on Ethereum. Great. So let me just get into the code. Cool. So I have a demo here that I've sort of kind of cooked up very quickly. I've sort of set up the repo and some of the code, but I'll just give you, if you want to do something like this, you would basically, run. I'm using Foundry here to develop this example. So you'd run Forge init to create a new sort of repo, and then you would install the Lagrange LPN contracts, so as a dependency. So I've already done that, and we'll get into the code. So this specific application we're going to deploy is called Pudgy Points. It's basically it's a contract that rewards or awards some points to any of the holders of a Pudgy Penguin NFT. And I think the important thing, we'll kind of start just at what are the dependencies. What is your contract when you're implementing it? What do you need to sort of implement to integrate with the Lagrange? So really, you just need to implement this LPN client v0, which comes from the SDK that you would have installed. And it's very simple. Really, the main thing that it does for you is it sends the callback, with the results of your query to your contract. So all you really have to do is implement this function, this process callback function. And the main reason why we sort of have this is one, to know where to send the callback, to send the result from our smart contract to yours, but also to sort of confirm that only our smart contract can give you this callback. And the reason is, in our smart contract, we're going to verify this proof that we computed on chain. And once that's verified, we can send it to you, and you can trust us, but you don't want anyone to send it to you, right? Unless they would have verified the proof as well. Great. So it's very simple. We just need to implement this process callback, which will come from the registry. And maybe I'll just give a very quick overview of this registry contract, just very quickly, because it's not too complicated, sort of what it does. So let's see, LPN registry. So great. I won't go into too much detail. I'll just point out the important parts. So one thing is you do need to pay sort of a gas fee, and it would vary depending on the chain you're on. On L2, it's gonna be very cheap. It's roughly 50 cents currently. And the gas fee is really just paying for us to send the proof and the result on chain, and then verify it, and also call your contract. So this should cover all of that there. And then we do so when you're sending a query, we need to validate it, we should validate it to make sure it's well formed, let's say, before trying to process it sort of off chain. So these are just sort of standard, sanity checks. The big one also being that the contract that you want to query, i.e. Pudgy Penguins, is something that we've sort of indexed and that we're kind of proving block by block, so so we can answer it. So that's one check. And we have this registration, again, very simple, just emits an event. Currently it's whitelisted for v0, but this will be open, for anyone to register in v1, and of course sort of have an economic model around that as well. So then we just have kind of two functions. We have this request function, right, which is what you're going to call. And the request function is essentially, it's going to save some information about your query such that we can use it later when we're verifying the proof. We need to know that the proof that we're verifying is not only valid, but it actually corresponds to what you requested, right? So that, and another thing that we do, that we have to do on L2 is that really the only information that we need, aside from kind of what your query was, like the parameters of your query, the only other piece of information we need to validate, to verify the proof on chain, is a block hash that, right? And so this block hash is a block hash that would have, that corresponds to, the hash that we've used to compute these proofs. So on L2, or especially on OP stack, there's a precompile. It's sort of provided by OP stack to access the block hash of L1. Because I'll clarify, the block hash we need to use, it needs to correspond to the chain that the data is from, right? So OP stack lets you look up the most recent block hash, and so we basically just cache this here so we can use it later. But on Ethereum, we don't have to do that because you can look back 256 blocks in the history for a block hash. So that's not a problem there, but it's a small but important detail. And then there's this respond function. So this respond function is what our Oracle, our sort of relayer, it will call, and really anyone. You can see there's no permissions on this, right? So anyone can call this because we sort of have a proof, right? So it's sort of the data contained there. We're going to verify it. As long as anyone could have access to it, then anyone can send it. But in our case, we're sort of running a kind of component to do that. So yeah, and you can see there's not much going on other than this sort of Groth16 verifier process query, right? So this is where the verification happens. I won't go into that because then we'll be here all day. But you can look at it sort of on your own time to see exactly how that verifier is implemented and what it does. And then sort of once we've done that, we call your contract. That's this LPN callback. So we're going to call the client of the query, whoever sent it. In this case, you. And we'll just call it with the request ID as well as the results. Great. So that's overview of kind of the on-chain things, how things work from our side. And now we'll go into, as a developer, how it works in your contract, how you actually use this stuff. I won't go too much into sort of what's going on here. This is mostly application specific. You can define, what events you want to emit for, to see things off-chain or in a front end. There is one important is this points request sort of struct, and you can see a mapping here. So really, this is if you've used sort of other Oracle-based systems where it's sort of a request and a callback, this would be familiar. But essentially, there may be some context or data that we want to access when we get the callback, and that context likely came from when the request was made. So this points request, this could be anything that you need in your callback, but it's good to sort of save, in storage what the request was and what was the context. So this is an important piece. This is one of the steps you need to integrate. Is really just in your constructor, you need to pass the address of the registry, and this is well defined. It's in our docs. I have a script I'll show you as well, but it's consistent across kind of all chains. So it's sort of it's well defined, but you need to pass it. And then this is kind of this is really the main entry point of a user using your contract. So you're going to make a request, right? You're going to query something. And I have some checks here, in this case where this is sort of a points program that people can claim, right? So actually how this function works, anyone can send the transaction, but you can send it on behalf of someone else. So this claimer will be someone that you want to check, do they own a Pudgy Penguins NFT? And so I sort of have a check that, so they can't claim more than once. And in fact, I do this here, to sort of fail early, so we don't send a query and, we don't necessarily need the result if someone's already claimed. But really, I just want to point out what would really be important is to check any constraint like that in your application. You'd want to check it in the callback because it's sort of this asynchronous system, right? So you can imagine this could be successful up here, so you could sort of query multiple times and there will be a little bit of a delay, let's say about a minute. So if you don't check that constraint here, where you're updating it essentially, then you could have sort of a flaw in your logic. But yeah, otherwise, the interesting part is really this query. And I've sort of written these variables here to sort of make this read like SQL to make it more clear. So we essentially have a select token IDs from Pudgy Penguins where the owner equals the claimer from some block to another block, some block range. In our case, we just want to check, does someone own this an NFT, currently? So this will just be the latest block to the latest block on L1, of course, on the chain that we're querying from, or sorry, the chain that the data lives on that we want to query. And then offset right? Sort of standard SQL kind of parameter. And you'll see here, I'll just kind of point out this, it looks a bit complicated. It's really, this is just the address. And the reason it's bytes 32 is it's sort of a bit more generic to, you can imagine in the future that you would want to query any mapping that might have some key value. So it's bytes 32, but we're just sort of converting it, address all the way up to bytes 32. Great. So you send the query, you've specified, the gas fee, which is you can get from the contract. And of course, whoever's making this transaction has sent that gas fee. And then down here, when you process, you're going to get the callback in, let's say, a minute. And you're basically going to check. Obviously, you check to someone already claimed already. But really, and so then in here, you check, the length of the results. So the results in this case would be the token IDs, right? You imagine a select query, you're going to get an array, like rows, right, of different matches. And so really, we just care, are there any matches at all? And if there are, that means that they are a holder. And then we can award them some points. We check, we sort of store, they've already claimed it, we emit an event. And then we sort of delete this kind of temporary context that we don't need anymore. Cool. That's sort of it. And you can see on a repo, there's links as well. I'll put this example up there. There's other similar examples. Again, the query functionality is quite sort of simple, or the capabilities are a bit simple for V0, but you can already sort of think like what types of applications are possible when you have this ability to query from any chain, query any other chain of historical data, and not just do selects, but do aggregations, like sums, averages. So I'm really excited to get that functionality out because I like to build sort of fun smart contracts and love to do more with it. Great. And then I just have a script here. Basically, we're going to deploy that contract on base mainnet. And then we're going to actually run the claim function. And we're going to run it on behalf of Blur. Or we're going to pass Blur because we know that Blur owns, at least the smart contract holds Pudgy Penguin NFTs. So that should be valid and Blur should get some points. Great. So let's run that. So I have a make file. I believe my command is make base deploy. So let's run that. And we'll give it a minute. Great. And then I'll try to enter my password and do that incorrectly. We'll do it one more time. And I'll go very carefully this time. Great. Okay, so that's gonna send. I've already sort of deployed and verified it, and sort of sent this, so we can kind of look at that while this processes. So if I go here, so this is our sort of LPN registry contract on base. This is the Pudgy Points contract I deployed previously. Let's see, about an hour and a half ago. And so you see the request points. We can look at the logs and see exactly what was sent, right? So we just had this was emitted by the registry. It's sort of the parameters of the query. And then we have, our query here. So basically who sent it. And I think I may have modified this in the meantime. I think there's more information in the new version. But really, what we want to look for are sort of events emitted by this contract. So we can see this event came from the registry, or I think actually in this case, this came from us. So this is the result. These are sort of the NFT IDs. If I decode those, so those are, well, this was the request ID. Oh, sorry. No, these are our results. So, right. So you can see these are the sort of the token IDs that were kind of that first, the first 5 or so. And you can see the sort of points claimed And this would be the amount of points, I believe. Yeah, so 100 kind of ether worth, and the query itself. And so let's see. In the meantime, let me just switch back. Great. So my contract did deploy. It didn't verify. This is I think might take a bit of time, but we can still see it. So let me just go here and check that everything's kind of the same. So yeah, we can see the request points. This happened roughly a minute ago, and we will see if the results come back yet. So it looks like it has. Great. Yeah, you can see the respond function. That was from our registry contract. You can see sort of the query that came before and the points claim. So this was the query, and then this was sort of the callback. These two events. Great. So and again, we can look at some of these NFT IDs. We could check on OpenSea or something to sort of verify those are correct. But I think in a nutshell, that was the demo. I hope that gave you a good idea of how to use our V0, and sort of got the juices flowing in your brain of how you might use this, and maybe what you can do in the future very soon when we have this kind of full SQL capability.
Thanks.
Thanks a lot for that great presentation. Let's give the audience some time to digest with all the info you presented. I think you did a pretty good job. Is there anything you would want to add that you guys forgot to mention?
I'm good.
Okay, so like maybe another question, what would you like to see from developers building on top of EigenLayer? Maybe you can give them some inspiration around zk or, yeah. Yeah,
Jonathan, you want to take this or should I?
Yeah, well, I think, well, I'll just give a note about us and kind of where we are, the part that we didn't mention. So we're working right now to deploy as an AVS and EigenLayer. Nicolas mentioned that we can run this massive proving network and do everything sort of parallel, and this would be great to have operators running. And so we just sort of started our test net for the zk-coprocessor. Lagrange does have another AVS sort of live for the state committee's product, but for this product we just talked about, we started the test net yesterday, and we're looking to have mainnet for that sometime in the next couple of weeks. And then, like we said, V1 probably in a few months, 2 months, something like that. So at that point, you'll be able to do a lot more with these contracts. But even now, I would say take a look at the smart contracts repo. There's other examples there. I'm sure there's other interesting things you can do. You could mint NFTs for holders of Pudgy Penguins on sort of other chains. The LT Points program, and there's other things I've been thinking. Even with this sort of very early functionality, there must be some other cool things you can do with sort of reading NFT state, cross-chain.
I think it's quite cool that you get some data on another chain from an NFT. Then there's also like cross-chain utility, cross-chain perks.
Absolutely, because Ethereum, I mean, it could be any chain, but let's say Ethereum now, there's such like rich data and state there, but it's so expensive, to send transactions, and so on Base it probably costs you 20 cents or something. We also have Fractal and Mantle will be sort of live today, and there it's pennies, less than a cent to do this type of stuff. So yeah, it is really it's very powerful, kind of what we'll be able to do.
Yeah, there's one question I was wondering, is smart contracts and blockchain something I should learn to be an engineer, or it shouldn't be a priority? So maybe how important do you think is it to understand smart contracts and blockchain to contribute to a Web3 project from your point of view?
Yeah, I would say it is quite important. I think you don't have to be a Solidity expert or sort of learn all the tricks, all the gas optimizations, all that sort of thing. But I think being familiar with the blockchain, the sort of data structures, and over time even dabbling a little bit in cryptography and learning some primitives there, I think it is very valuable when you're building, if you're building stuff off chain that integrates with the blockchain somehow or reads the data. That's my take. But yeah, you wouldn't have to dive in and do something crazy in production for a smart contract, something super complicated. You can do things that are still quite simple on chain, but let you build interesting applications.
Yeah, that sounds very good. So I think that would be it. Like, you guys did a great job, and Nicolas, sorry once again, in terms of the presentation or slides.
No worries.
Yeah, but I think like it's good for the audience, like they can watch it even asynchronously. What's a good way to reach out to you guys?
Good point. We have a new Discord now, but I think, let's see if it's on the websites. Yeah, if you go to lagrange.dev, there is links to our Twitter, Discord at the bottom of the page, basically. So
Okay.
Lagrange.dev is the website, and there's like the Discord link at the bottom.
All right. So
I think that would be a good point of contact for us. We're trying to centralize all the questions from developers and figures here.
yeah, if you guys have any questions, hop on their Discord, join the Discord and ask them. So thank you very much, Nicolas and Jonathan, for joining us today. It was
Thank you.
super insightful and a great presentation. I hope the audience learned a lot. There will be more events like this. So also, guys, subscribe to our socials like our Binance Live and YouTube, and see you soon.
Great. Thanks a lot.
Thank you,
Bye-bye.
guys. Bye-bye.
Bye.
Take care.